So following up on our basic discussion of special relativity, I want now to talk about relativistic mechanics. Okay, so we have to introduce a couple of notions of this that we'll need later on. So let's say you move at a velocity which we'll write here as u. Okay, as compared to a ground clock, your time goes slower. Okay, so so if you have a ground clock interval delta t, so just I'll write it dt. You've got your own time, moves with you, your so-called proper time. Is d tau, which is, you remember this factor of 1 over gamma, so we'll just write it explicitly here, 1 minus u squared over c squared square root with the dt. Okay, so this is your proper time as compared to the ground clock time. Now, for an observer on the ground, your velocity, so ground observer, your velocity is by definition the rate of change of your position which we'll denote as L vector with respect to ground time. Okay, so there would be your velocity u, now with a direction, that would be measured by measuring a certain differential of your position with respect to a differential time on the ground clock. Okay, and this is called the ordinary velocity. Okay, but there's a bit of a bugger in this definition here, because if you think of doing Lorentz transformation, then both spatial coordinates change, but also the time coordinate changes. So it's like not so nice. A better object to consider is really another object, which is called the proper velocity. Which is by definition, so we'll write it as this eta bold, is by definition the rate of change of your position as measured on the ground with your clock as measured by yourself. So it's like a hybrid quantity, because you're measuring the coordinates on the ground, but you're using your clock as you're moving as the time measure. Okay. The relationship between proper and ground velocity is quite simple. It's just that eta is equal to just gamma times u. Okay, so the proper velocity is just gamma times the ordinary velocity. Okay, so the nice thing about this proper velocity is that transforms well under Lorentz transformations. Okay, so that's the advantage of using this thing. Now we can do a little bit more here. We can add a zeroth component to this 3 vector here. Okay, and this zeroth component is by definition the rate of change of this zeroth coordinate, which was our time-like coordinate that we had with respect to proper time. Okay, so this is really c times dt d tau. But we know the relationship between t and tau is just this, this gamma. So this is really just gamma c, right? So c divided by 1 minus u squared over c squared square root. Okay, so this allows us to define another 4 vector, which carries a few names. So it's either called the 4 velocity or the proper velocity vector. Okay, it's simply defined by saying that eta mu is 0, 1, 2, 3. By definition, it's just dx mu d tau, where tau, once again, is your proper time. Okay? And it transforms nicely as if you go to another coordinate system, the new 4 velocity is just going to be given by the Lorentz transformation matrix like this, acting on your original coordinates. Okay, again, using the Einstein convention between them. Once again, this works well because the denominator here is an invariant under the Lorentz transformations. Okay. There's, of course, a lot of pain associated to ordinary coordinates. You can find equations in Griffiths to show that ordinary velocities obey these kind of cumbersome transformation laws, but I'm not going to spend time on this here because yeah, I'm sure you're kind of already familiar with these things. Now, this leads us now to talk about relativistic energy and momentum. So what do we want? Let's start first of all by the relativistic momentum. This is defined as m times the proper, sorry, that's the wrong symbol, times the proper velocity eta, okay? And this is really just m with your u divided by 1 minus u squared over c squared. Like this, okay? And the relativistic energy, this is by definition mc squared divided by 1 minus u squared over c squared, and again square root. Okay, and these are nicely combined into the energy momentum for vector p mu. Notice the change of notation, right? This was a 3 vector, but now this is a 4 vector. By definition, it's just m with the proper velocity like this. Okay? So that's our energy momentum for vector. So if the object is stationary, the energy is then the so-called rest energy, E at rest is equal to mc squared. Okay, which possibly the most famous equation in the whole of physics. At least the lay people, that's the one equation they might know. They don't understand, but at least they've heard of it and they've seen it. Okay, that means that when you're in motion, you can take the kinetic energy, so kinetic energy, E kinetic, to be the difference between the energy and the rest energy. Okay, and this is just mc squared with, yeah, let's just write it as gamma minus 1, or 1 over 1 minus u squared over c squared square root minus 1. Okay, and you know the story. You can easily do a simple Taylor expansion of this thing, and you just get 1/2 m u squared plus then a relativistic correction that looks like this. Sorry, c squared like this. Sorry, that is a 4. mu squared over c4 plus higher order corrections like this. Okay. The reason why energy is so important is because of conservation laws, and the statement is that the total relativistic energy and momentum is conserved. Okay, so this this quantity here, E squared minus C squared P squared, would be M squared C4, and you see that's an invariant irrespective of which frame you're measuring that in. Okay, so that's a kind of simple, summary of things that you've probably all very well studied in the first year. In the book, there are lots of examples about relativistic kinematics. I will leave those aside for now because we want to focus much more on things that pertain really directly to the electrodynamics that we've been studying.